Next generation nuclear weapons. This video is intended to provide as much information about the fourth generation of nuclear weapons. But in order to understand this next generation, it is important to explain the previous generation of weapons to provide context to what the advantages are for the fourth generation of nuclear weapons. The first generation of nuclear weapons were the fission-type weapons that were first used on the cities of Hiroshima and Nagasaki. These weapons used nuclear fission to generate tremendous amounts of destructive energy. Nuclear fission works by firing a neutron at the nucleus of a heavy element like uranium. The impact causes the atom to split into two lighter elements, which in turn releases energy in the form of X-rays, neutrons, and other particles. Approximately 80% of the energy released is in the form of soft X-rays, and 20% is released in the form of neutrons and other particles. In an atmosphere, the X-rays are attenuated quickly and turned into heat, which in turn produces a shockwave. This shockwave is the primary mechanism for destroying unarmored targets in a large area surrounding the point of detonation. There were two designs of fission weapons. The gun-type fission bomb worked by firing a subcritical slug of uranium-235 at another subcritical mass of uranium-235. When brought close together, the radiation of slow-moving neutrons will cause nuclear fission. However, they have to be brought together very quickly, otherwise the reaction will result in a fizzle, in which only a small amount of the fissionable material actually undergoes nuclear fission, greatly reducing the explosive yield. While this design is very easy to construct, it's very dangerous, and the two masses of uranium have to be kept away from each other before deployment, or else fission will take place. In addition, plutonium cannot be used in this design. Only uranium-235 may be used. The little Boyd bomb which was dropped on Hiroshima was the gun-type design. The second design is known as an implosion-type fission bomb. This design also produces greater yields than gun-type. For these reasons, the gun-type design has been phased out, and now the implosion type is the preferred method of achieving nuclear fission. The second generation of nuclear weapons utilized nuclear fusion to boost the explosive yield dramatically. These weapons are often referred to as a hydrogen bomb or thermonuclear weapons. Fusion is the opposite of fission. Instead of a heavy element being split into two smaller elements, fusion joins two smaller elements into one heavier element. This is possible thanks to the strong nuclear force. The strong nuclear force is what keeps a nucleus together. Protons have a positive charge and normally would repel each other due to like charges repelling each other. But the strong nuclear force keeps protons joined together at an atom's nucleus along with neutrally charged neutrons. Normally, the electromagnetic force repels the nuclei of atoms due to their mutual positive charge repelling each other. However, if the nuclei were forced together close enough, the strong nuclear force would take over and force two nuclei to join into a heavier element. This act of fusing releases tremendous amounts of energy, mostly in the form of high-energy neutrons. The fusion isotopes used in thermonuclear weapons release approximately 80% neutrons and 20% X-rays and other particles. The question is, how do you get the nuclei of atoms close enough to fuse? In the core of our Sun, sheer heat and pressure causes atoms to be forced into close proximity of each other and enter a highly excited state where they are likely to collide with each other and undergo nuclear fusion. In thermonuclear weapons, a fission bomb is used to create intense heat and pressure, enough to cause the fusion isotopes to undergo nuclear fusion. Thermonuclear weapons utilize the Teller-Ulam design, which separates the fission and fusion parts. The fission primary uses an implosion method described before and catalyzes the fusion secondary. This in turn releases tremendous amounts of neutrons at high velocity. This phenomenon can be taken advantage of by a method called fast fission. Normally, U-238 or depleted uranium will not undergo nuclear fission. Slow-moving neutrons are not sufficient enough to cause this rather abundant isotope of uranium to split. However, fast-moving neutrons will, and so a layer of depleted uranium is kept around the fusion fuel to undergo fast fission when the fusion isotopes undergo fusion. This metallic layer surrounding the fusion fuel is called a tamper. While a tamper is normally made out of depleted uranium to maximize total yield, it can be made out of other materials which will be described later. So the Teller-Ulam design utilizes three different stages: the fission primary, the fusion secondary, and the third fission stage. This design is the most efficient design developed so far, and today virtually all nuclear weapons use this design. Third-generation nuclear weapons are specialized versions of thermonuclear weapons, and most of them exist only on paper, but almost all of them are feasible to construct with current technologies. One type is a weapon called a neutron bomb. This weapon removes the depleted uranium tamper on a thermonuclear weapon with a material that is mostly transparent to neutrons. The idea is to maximize the neutron flux emitted by the bomb so that the highly penetrative neutrons can pass through armored vehicles and buildings to kill personnel that would normally be protected from the intense heat and radiation produced from a nuclear explosion. A common misconception is that neutron bombs will not produce an explosion at all and will leave infrastructure intact while only killing life forms. This is not true, as most designs still have yields in the kiloton range, which would produce a very powerful explosion. The idea is simply to kill targets protected by armor. Another type of weapon is known as the cobalt bomb. The idea of this weapon is to contaminate an area with dangerous and long-lasting radioactive fallout. The depleted uranium tamper surrounding a thermonuclear weapon's fusion fuel is replaced by a tamper made out of ordinary cobalt. The flux of neutrons released in the fusion reaction causes the cobalt to transmute into cobalt-60, which is intensely radioactive, with a half-life of about 5.27 years. Such a weapon would result in the area it is detonated in to be severely contaminated for many years and could not be reoccupied by friendly or enemy forces. As a result, the cobalt bomb would serve mostly as an area denial weapon. The tamper can be replaced with other materials such as gold even to produce different radioactive isotopes with different half-lives. These weapons are generally referred to as salted bombs. During the Reagan administration, work went into producing an X-ray laser designed to shoot down ICBMs. The design used a nuclear device which would release most of its energy in the form of X-rays to pump laser media that would focus the X-rays into a number of collimated beams. Since the nuclear explosion would subsequently destroy the surrounding laser hardware, the device would only be good for a single usage. But a single nuclear charge could be used to pump multiple X-ray beams, which could shoot down numerous ICBMs at once. In the 1960s, a new type of propulsion device was proposed for space vehicles called the Orion drive. Instead of a traditional rocket, the Orion drive would utilize a series of nuclear explosions placed behind the spaceship to provide propulsion. It's essentially the same principle behind what makes a tin can move when you place a firecracker underneath it. However, using an unmodified nuclear charge would result in 90% of the energy released in the explosion to be wasted, instead of providing thrust to the spaceship. To maximize efficiency, the energy released had to be directed toward the pusher plate beneath the spaceship to provide thrust. The result is a shaped nuclear charge. The nuclear device is enclosed by a material that is opaque to X-rays, such as uranium, but with an opening at the top so that the X-rays are forced to leave through that opening. The X-rays then bombard a mass of beryllium oxide, which provides heat to turn another mass of tungsten into plasma. This plasma jet is then directed at the spaceship's pusher plate. 85% of the nuclear charge's energy is confined into a cone of about 22.5 degrees. However, this design can also be used directly as a weapon if the cone were reduced even further and the plasma velocity were increased. This would result in a culminated particle beam that would be capable of destroying armored vehicles and reinforced bunkers as well as other targets. Although the exact material to achieve such effects is still highly classified, it is known that using an element with a low atomic number to generate a plasma jet will produce desirable results. Such a weapon is referred to as a Casaba howitzer. Finally, we get to the next generation of nuclear weapons, or the fourth generation nuclear weapons. These devices will be fusion nuclear warheads triggered by a non-fission primary. There are several reasons why a non-fission trigger is desired. One of them is the significantly radioactive fallout produced. Dangerous radioactive fallout makes fission weapons undesirable for a variety of reasons. They can't be used tactically due to the contamination of the environment that the fission weapon was detonated in. It makes it impossible for friendly troops to occupy the territory. Radioactive pollution is one of the primary reasons for political condemnation of any use of nuclear weapons. As such, fission-based nukes can almost never be used in any capacity due to fear of an outcry from political and public domains. If a weapon were devised that limits the radioactive contaminants to a minimum, their use could be seen as more politically acceptable for tactical use. Nuclear weapons have been envisioned as a method of penetrating hardened bunkers or underground military facilities. A problem with Earth-penetrating weapons that use fission is the enhanced radioactive debris produced from the fission reactions interacting with the surrounding environment, turning debris into dangerous radioactive fallout. In addition, a fraction of the fissionable reactions that did not undergo nuclear fission will be in the area that the EPW was detonated into, which can then be recovered by terrorists or enemy troops and reused in nuclear devices. With fourth-generation nuclear weapons, both of these concerns are reduced or eliminated. Another advantage of a non-fission trigger is the ability for the weapon to be of any yield. Fission weapons have their minimum yield restricted by the critical mass of the fissionable materials. Fourth-generation nuclear weapons will fill in the gap between the minimum yield of fission weapons and the maximum yield of conventional weapons. Because the energy-to-mass ratio of fusion is so high, it's theoretically possible to have very small weapons with very powerful yields. At present, the three most feasible means to trigger a pellet of nuclear fission would be high-powered lasers, nuclear isomers, and antimatter. High-powered lasers can be used to compress a pellet of nuclear fuel so that the pressure and heat generated is sufficient for nuclear fusion to occur. However, at present, the energy being used to power these lasers exceeds the amount of energy being released by the fusion reactions. In the future, more advanced laser technology with improved efficiencies will mitigate this problem significantly. However, the surrounding hardware for the lasers is still quite massive and will remain so for the foreseeable future. This makes this method of fusion unattractive for fourth-generation nuclear warheads. Nuclear isomers are excited states of an atom's nucleus. Electrons surrounding an atom's nucleus can attain an excited energy state. When excited, electrons will move to a higher level electron shell. When they return to a lower level shell, they emit a photon. It was theorized by physicists that perhaps the nucleons in an atomic nucleus could also attain an excited state. It turns out that this is true, and excited nucleons can emit much more energy than excited electrons can, and they emit this energy in the form of energetic gamma rays. The hafnium isomer hafnium-178M2 has an extremely high energy density and a half-life of 31 years. The question, though, is how to get the nuclear isomer to release its energy on demand. Many experiments have attempted to accomplish this, but thus far none have been successful. The final method to achieve fusion without a fission trigger is to use antimatter. Antimatter are particles of mass that are composed of antiparticles with corresponding charges that are the opposite of what their normal matter counterparts are. For example, a positron that is positively charged while an electron is negatively charged. An antiproton is negatively charged while a proton is positively charged. The remarkable phenomena that antimatter brings is the fact that when it collides with normal matter, they both annihilate and release energy equivalent to their rest mass. As such, a few kilograms of fissile material in a hydrogen bomb can be replaced by a few micrograms of antimatter instead. Because their energy density is so high and catalyzing the energy release is feasible, antimatter is attractive for triggering a nuclear fusion reaction. However, there are some problems which must be overcome before antimatter is used in fusion weapons. The main concern is producing antimatter in the first place. At present, the production of antimatter is horribly inefficient, but with advances in engineering, efficiency of producing antimatter could improve to about 0.01% in the foreseeable future. This number sounds abysmal, but it's in fact thousands of times better than what is currently being achieved. Keep in mind that antimatter is not being used as the main source of energy in bombs, but rather as a trigger for fusion, which is the main source of the weapon's power. The second concern is how to contain the antimatter. Since it instantly annihilates with normal matter, active measures have to be taken to ensure that the weapon will not prematurely detonate. For weapons, the best method to store the antimatter is in a condensed material in which certain areas inside will function as micro or nano-sized traps where antimatter could be confined away from normal matter. The traps will be metastable but should be robust and rugged enough to be used in weapons. In fact, they could be so rugged that there is no moving parts at all, and it will be completely solid state. This would allow them to be used in earth-penetrating weapons that require a high degree of robustness. This technology will require major advances in nanotechnology, but it's entirely feasible to achieve. Using an antimatter trigger, a fusion weapon could be no larger than a golf ball, but have yields equal to several tons of TNT while producing very little radioactive fallout. This makes fourth-generation nuclear weapons useful as tactical weapons that can be used on the battlefield. Fusion using deuterium and tritium isotopes release most of its energy in the form of energetic neutrons. About 80% of the energy released from a DT fusion will be in the form of neutrons, while about 20% will be in the form of X-rays. This increased neutron flux will increase the amount of energy coupled to desired hardened targets and ensure their destruction. In second-generation nuclear weapons, energy is mostly coupled to targets indirectly through atmospheric medium, which produces a shock wave. This is sufficient to destroy lightly armored targets, but is insufficient to destroy hardened or armored targets. In fourth-generation weapons, energy is coupled directly to colliding the target with an intense neutron flux, which will dramatically increase the energy coupled. Energy coupling can be further increased by creating shaped nuclear charges. Normally, an unmodified charge detonated near a target will couple at most 50% of its energy released by the weapon. The other 50% is wasted unless shaped and directed against targets. A fusion reaction can forge one or more projectiles that can essentially be described as bullets being propelled by fusion instead of smokeless powder. These projectiles could potentially be aimed at multiple targets and allow a single warhead to destroy several targets at once. The backwards going energy that is normally not directed at the target can be used to superheat a working fluid and form a powerful plasma jet moving at high velocity directed at the target. Both of these phenomena working in tandem will dramatically increase target coupling over conventional weapons and second-generation nukes. So as we can see, fourth-generation nuclear weapons offer numerous advantages over previous-generation nukes and conventional weapons. In fact, fourth-generation nukes may render conventional charges completely obsolete if mass production is ever achieved. And that concludes this analysis on fourth-generation nuclear weapons.